Hi, I'm Dick Seitz.
And I'm Dirk Meyer.
And we're going to talk today about alpha. In discussing alpha, we make the distinction between the architecture as a paper document and the various implementations. I'm going to talk about the architecture.
And then I'll be back a little bit later to talk about the first implementation of that architecture.
I'm going to talk about the alpha architecture, about the goals, an overview of the architecture, about the things that are different from other RISC architectures, and then about some of the problems that we addressed in designing the architecture and how we thought about them. Rich Wittick and I are the co-architects for alpha. My part of the alpha design has been influenced substantially by three other architects, Fred Brooks, John Koch, and Seymour Cray. When we started the alpha project in 1988, we set four goals for the architecture: performance, longevity, scalability, and generality. In performance, we wanted the architecture to allow implementations that would be faster than anything else in the industry each year for the foreseeable future. That performance goal reflects itself in a number of the details of the architecture, as I'll show you in a few minutes. For longevity, we wanted the architecture to last 15 or 20 or 25 years, much longer than a 10-year design cycle. And that longevity goal implied a number of design decisions if we were honest about meeting that goal. The first design decision is that it had to be a 64-bit architecture. All the 32-bit architectures will run out of address bits sometime in the next 10 or 15 or 20 years. In fact, in designing the first chip, we ran out of address bits on VAXes last year. In addition to being a 64-bit architecture, the longevity goal implied that implementations over the course of 2 decades would have to scale up in performance. We looked at how the scaling could happen. The first chip runs at 200 megahertz, 5 nanosecond cycle. It looked unlikely that the chip speed, clock speed, would improve by a factor of 1,000 over 25 years. But the industry curves say that the implementation performance does need to improve by a factor of 1,000 if the architecture is going to last that long. We thought it was realistic for the clock speed to improve by a factor of 10. So we looked for other places to pick up the other factor of 100. If the clock speed isn't going to pick up by more than a factor of 10, then to gain more performance, you have to do more work in every clock cycle. So very early in the design, we settled on the idea that the architecture would have to gracefully allow multiple instruction issue, that it would be necessary for the longevity goal and the performance goals for the architecture to allow many instructions to be started every clock cycle. We thought realistically over the course of a few decades, perhaps using compilers that our children build, that compiler technology could pick up a factor of 10 using multiple instruction issue. That still left us a factor of 10 short. So we looked at where else implementations could pick up performance, and the only other way we saw was to have multiple processors, to have perhaps as many as 10 processors in a box 25 years from now executing pieces of a common program. So we focused the architecture, just because of the longevity and the scalability goals, on those 3 points of very fast clock cycle, multiple instruction issue, and multiple processors. Finally, we designed the architecture to be general. It's not just a Unix hotbox. It's designed to be able to run VMS, to be able to run OSF1, to be able to run other operating systems, to track different computing paradigms as the industry changes over the next 5 or 10 or 20 years. We also designed it to support a variety of computer languages, not just Fortran and C, but also COBOL, Pascal, Ada, BASIC, lots of other languages. And finally, in looking at bringing a new architecture to the market, we focused on migrating our current customers from VAXes and from MIPS DEC stations to the new architecture We rejected things like hardware compatibility mode in favor of doing software translation of binary images and doing compilers with compatible front ends for source code recompilation. Here's an overview of the architecture. It looks very much like other RISC machines on the surface. It's a 64-bit load store RISC machine. Instructions are 32 bits wide. They describe operations on 1, 2, 4, or 8-byte integers. They describe operations on VAX single precision and double precision floating point. Also IEEE single precision and double precision floating point. There are 32 integer registers, each of 64 bits. One of those is hardwired to 0, and one of them is used as a stack pointer. There are also 32 floating point registers, each 64 bits, and one of those is hardwired to 0. In addition, the program counter is a full 64-bit virtual address. And there are a number of other counters and registers to allow writing real operating system multitasking software. Things like a cycle counter for performance studies, floating point status register for IEEE rounding modes and status bits. 64-bit virtual addresses are used throughout the architecture, although implementations are allowed to implement a subset of the virtual address space, so long as they check the high-order unimplemented bits for validity. The instruction formats are very straightforward. There's a 6-bit opcode in every instruction. The first format has call PAL instructions, has a 26-bit function field that describes one of a few dozen privileged subroutines that are used to execute a number of the complex operations that operating systems are built on top of. I'll discuss those operations in a few minutes. The branch instructions have the 6-bit opcode and then a 5-bit register number to be tested. That can be tested for positive, negative, 0, non-zero. In the case of the integer registers, even and odd. And then there's a 21-bit sign displacement field that's actually a long word displacement. It describes, relative to the branch instruction, a target address instruction anywhere within plus or minus 4 megabytes. The memory formats have the 6-bit opcode and then 2 register fields of 5 bits each. The first field specifies the register to be loaded or stored. The second field specifies the base register for the memory address. And the remaining field specifies a 16-bit displacement, sign displacement from the base register. The last format is used for operations between registers, 6-bit opcode, 2 source registers, a function field that's really an extension of the opcode, and then a destination register. All the operations read 2 registers and write 1 register. They read all 64 bits of the registers and they write all 64 bits of the registers. One of the simplest way of characterizing how this architecture is different from other architectures is by what's not there. There are no condition codes in the alpha architecture because they get in the way of doing multiple issue. If you issue 6 instructions at once and they all potentially set the condition codes, and there's really only one condition code register, then you have to build a lot of very messy hardware to sort out which of those 6 instructions actually sets the condition code register. And if the 4th of those takes an overflow, and then in fact you discover on the fly that the 3rd one has to set the condition code register, getting that right is very messy. So condition code registers are an example of a design technique that's difficult to use when you're planning on multiple instruction issue. So we don't have it in alpha. In a similar way, we don't have fixed registers for operations such as string pointers or multiply or divide. Some architectures have a multiplier quotient register or dedicated registers for other operations. The problem with that is if you try to launch like 4 instructions at once and they're all multiplies and there's only one multiplier quotient register, it's a bottleneck. You either have to build hardware that shadows multiple copies of the MQ register, or you can't launch multiple multiplies. So we simply don't have it, and all of the operations are completely general between the general registers. Finally, we don't have byte writes. If you look at implementations of writing a single byte to memory, somewhere in real implementations, memory is accessed in complete memory words, which are typically 4 or 8 bytes wide. Updating a single byte in a memory word somewhere involves reading the entire memory word, possibly correcting a single bit or double bit error if the memory system has error correction, then updating the single byte, and then recalculating any error correction or parity bits, and then finally writing the entire memory word. And that read, modify, write is really a sequence. And if it's implemented in hardware, in the memory board or in the CPU chip near the pins, wherever it's implemented, there's a tendency to only have one implementation of that sequencing hardware. And that makes it difficult then to launch 6 independent byte writes and to have them run in parallel. Again, the byte write logic becomes a bottleneck. So we took the fairly radical move in alpha of not having byte writes. Instead, there are carefully tuned instruction sequences that allow a program to do the read, modify, write as a load, an in-register modify, and then a store. And we included in the architecture enough design information to allow programs to do single byte updates within the same memory word, even in the face of other processors updating adjacent bytes in that memory word. And that can all work, and we expect over the course of a couple decades that removing that bottleneck will allow much faster byte write or byte manipulation programs than some other architectures that have an instruction that looks like it would help instead. Finally, we tried to avoid having first implementation artifacts. In contrast to doing a chip design and shipping the first chip, and if it's successful, then designing another one and shipping that, and it's a little bit different. We tried to design into the architecture solutions to all of the design problems we were aware of, even when that made the first chip implementation more difficult. Finally, we have included in the architecture careful support for multiprocessing. One of the design issues in multiprocessing is how to do atomic updates in memory between shared memory locations for multiple processors. We picked a paradigm of load locked, modify, store conditional that is also used in the MIPS R4000 architecture. That particular paradigm we chose because it's the only thing we could find that would scale up with processor speed over a couple decades. The idea is to do a load instruction, but using load locked, which remembers a few bits of state, then modify by doing an add or an or whatever the modification is in registers, and then do a store conditional instruction back to the shared memory location. If that entire sequence from the load locked through the modify to the store conditional, if that sequence runs with no interrupts and no exceptions and no interfering write from another processor, then the store conditional stores and leaves a bit in a register for the program to test to determine that the store actually occurred. If anything goes wrong, if there's an interrupt in the middle, if there's an exception on any of the operations, or if there's an interfering write from another processor, then the store conditional doesn't store, and instead sets the bit saying that it did not store. And eventually then the program needs to branch on that bit and go back around and start again with the load locked, retry the modification in the store conditional. When the entire sequence runs to completion, then in fact an atomic update has been done with no interference. So there are two advantages to this paradigm. First is that in the absence of an interfering write, the entire sequence of load lock, byte modify, store conditional can be done inside of an on-chip processor cache. The other advantage is that multiple processors can be doing independent sequences in parallel. There's no common lock bit somewhere in a shared memory system. For multiple processor support, we also included design around read-write ordering. Rather than the traditional strict read-write ordering, we specified that in the alpha architecture, from the point of view of a second processor, reads and writes launched by a first processor can arrive at the second processor in an arbitrary order. And then we included a memory barrier instruction to limit the permutations allowed in an implementation. I'll talk about that more in a few minutes. And finally, there's the usual number of registers for writing real software to keep track of which processor you're running on and thread-specific context. Here's a few things that are different in the alpha architecture compared to traditional RISC architectures. First, we tried to avoid first implementation difficulties and instead to do clean features that we hope will last many decades. For example, rather than architecting strict read-write ordering, as I just talked about, we architected arbitrary read-write ordering between processors and a memory barrier as a mechanism to specify the ordering exactly when it's needed. It's possible that other architectures that specify strict read-write ordering will find that that's a performance bottleneck over the coming decades. We also looked at issues like branch prediction and bearing the latency of branches. Rather than doing something like a branch delay slot that could bury one cycle this year or maybe 2 cycles, we looked at the long term and said that that's a technique that will not scale up well for a couple decades and will not scale well with multiple instruction issue. So we looked at other ways of solving branch latency problems. Similarly, we don't have in alpha complex instructions that do multiple operations, such as a multiply-add operation, which is really 2 operations in one instruction. We instead seriously designed to allow implementations to gracefully do multiple instruction issue. We believe that through multiple instruction issue, the same effects that you get with the complex combined instructions can be achieved in alpha, but achieved in a more straightforward way over the coming decades. We also designed a hazard-free architecture. This means that if an instruction writes to a register and a later instruction reads from that register, that the reading instruction always gets the written value, that implementations must implement whatever pipeline interlocks or scoreboarding are necessary to deliver the same results on all implementations, that there are no hazards in some implementations where a register can be read too soon and get an old value and be not binary compatible with a different implementation with different timing where the register turns out to be read later and get a new value. We also designed for the alpha architecture to have minimal global state. We've discovered, particularly in implementing VAXes, that having global state bits such as interrupt enables or rounding mode bits gets in the way of building very fast pipeline implementations. The tendency is when global state bits are changed to completely drain the pipeline, change the global state bits, and then restart the pipeline in order to guarantee that subsequent instructions see the state change and that previously issued instructions don't see the state change. And that draining and restarting of the pipelines eventually becomes a performance bottleneck, particularly if the state bits need to be saved and restored at every subroutine boundary. So rather than having global state bits, we designed to minimize them and instead put in every instruction things like interrupt enable bits or rounding mode bits. And the entire instruction and its local state can then be pipelined with no drains. We also have no mode bit, such as a 32-bit mode versus 64-bit mode, or VAX floating point versus IEEE floating point. This again minimizes the hardware complexity and maximizes the fraction of time that the pipeline can be kept full. As we were doing the architecture design, we kept in mind a number of implementation issues in terms of keeping many operations going simultaneously, having pipelined implementations, having long memory latencies that would grow with time. So we included a number of features such as specifying imprecise arithmetic exceptions rather than precise ones as an enabling technology to allow multiple instruction issue to be done gracefully without a lot of hardware overhead. We also included things like prefetching operations as a mechanism to cover some of the main memory latencies that we anticipate over the coming years. Finally, we included in the design a discussion of hardware-software agreements, of suggested ground rules for hardware implementers and also for software implementers, so that to the extent that both groups use the same ground rules, you end up with very high-performance implementations running high-performance software with very little work. One of the things that's different about the alpha architecture is the existence of PAL code. PAL stands for Privileged Architecture Library. It's a set of privileged subroutines, a lot like the basic input-output system in an IBM PC. They perform specified functions, but how they are implemented inside the subroutines can vary from one implementation to another. The specified functions are the complex operations that an operating system is built on top of, such as taking or returning from an interrupt or exception, or loading the memory management registers, or context switching. The PAL subroutines run with the interrupts turned off, and they may have implementation-specific access to physical hardware registers. There's a different set of PAL code for each operating system that allows the operating system to run on what's really an extended machine. For example, the port of VMS to alpha runs with a set of PAL code that provides VAX-like 32 interrupt levels and 4 memory management modes and a number of the complex operations that build interrupt vectors and include interlocked queue instructions. By having all of those in software, the actual alpha hardware is quite simple, but the VMS port took 2 or 3 years less than if VMS had been completely rewritten to avoid using those VAX features. In a similar way, the OSF1 operating system runs with its PAL code that presents to the operating system a simple Unix-like view of the world that does not have 32 interrupt modes. It has 8 interrupt modes and a number of other memory mapping features that many Unix systems are used to. In a similar way, the Windows NT operating system has its own PAL code that presents a view of the world that's culturally compatible with the 486 and the MIPS NT implementations. So those are some of the things in the alpha architecture that are different from other RISC architectures. Now I'm going to talk about a number of the design problems we had in trying to build a fast architecture to allow fast implementations. The first design problem is branch latency. The problem is when there's a discontinuity in the instruction stream, when a branch goes off to some other instruction, how to bury the time that must occur in real implementations before fetching the target instruction. Some implementations or some architectures specify branch delay slots in which after a branch is executed, the following instruction is also executed on the theory that in real implementations it's already been prefetched, so executing it is almost free, and it can cover up a cycle of latency while the target address is being fetched. That was a good design technique in 1988, but already we've reached the point where in real implementations that are quite fast, the branch latency that you need to cover up is 2 or 3 cycles instead of just 1 cycle. And an architected branch delay slot can only bury 1 cycle. In addition, branch delay slots don't make any sense when you are anticipating implementations that issue multiple instructions. And different implementations issue different numbers of instructions. For example, if you have an implementation that issues a peak of 3 instructions every cycle, and you have a branch delay slot that specifies 1 instruction is executed after each branch, then after every branch, the other 2 potential issue slots have to be wasted. You can only issue 1 of those 3 following instructions. Now, if branches occur about every 8 instructions, that can be quite a performance bottleneck. So rather than branch delay slots, we went back to the original problem of covering branch latency and looked for other solutions that we thought would scale well for a couple decades. And we didn't find any magic bullets. So instead, we approached covering branch latency on 3 different fronts. First, we architected branch prediction hits for two-way branches. The rule is that a two-way branch that is a forward branch is predicted not to be taken, and a two-way branch that's a backward branch is predicted to be taken. To the extent that the hardware implementers and the compiler writers follow the same rule, you get a very fast, very simple implementation that involves less hardware than branch prediction caches or things like that. For branches that have calculated targets, such as some subroutine calls or case statements or subroutine returns, there were bits left over in those instructions, so we use those bits as hints to the implementation about where the most likely target is. The low 14 bits of those branch instructions can be used to directly drive an instruction cache with the address of the most likely target. Because they are hints, implementations need not use them. Also because they are hints, if the hint is wrong, implementations must eventually, although perhaps more slowly, fetch the correctly specified target and actually branch to it. We also specified in those hints whether a given calculated branch was a subroutine call or subroutine return or neither. And that's enough information for an implementation to run a small stack of likely subroutine return addresses. And in fact, as Dirk will talk about in the first EV4 implementation, there is a 4-level subroutine return stack. That allows an implementation, when it encounters a subroutine return, to pull off the top of that implementation stack the most likely iCache address to fetch from, and under good circumstances have subroutine returns take 0 or 1 cycles. That's an example of how we thought about problems, looked at existing solutions in the marketplace, asked the question of whether they would scale well over the coming decades. When the answer was yes, we used them and did not deviate from conventional RISC architectures. When the answer was no, we said, what problem are these techniques solving? Go back and look at the problem with a clean sheet of paper and say, how else could the problem be solved in a way that would scale well over a couple decades? The last thing we did in trying to bury branch latency is to include conditional move instructions, which test a register and, depending on the result of the test, conditionally move a second register to a third register. These can be used for simple cases of testing end effects or doing maximum or minimum. And when they're used, they completely eliminate branches. And by eliminating branches, eliminate the issues of branch delays or branch latencies, and also, in fact, make basic blocks bigger and allow compilers to do more optimization and more code movement. So in summary, we rejected the traditional branch delay slots because they're incompatible with multiple instruction issue and with scaling up performance over many decades. We instead looked at fresh mechanisms that would give the same effect. Another design problem we looked at was how to handle arithmetic exceptions, things like overflows or divide by 0. Some architectures specify precise exceptions in which if an instruction gets an arithmetic exception, the following instructions must not have executed. Now that makes it very difficult to do things like 4-way instruction issue. You either cannot issue multiple instructions that could possibly get arithmetic exceptions, or you have to issue them and build a bunch of hardware, things like trap silos, that back out of the instructions that really should not have happened if you issue 4 and the second one overflows. So rather than specifying precise arithmetic exceptions, we specified imprecise arithmetic exceptions. We said, if you get an overflow, you find out about it later. Because the architecture is not tied to any particular implementation, the architecture doesn't say how much later. It just says later. It's the Cray 1 model of exception handling. But there are completely legitimate reasons for people to want to get precise exceptions. So we also included a trap barrier instruction that specifies of all the instructions that have been issued, at the barrier, all the preceding instructions must deliver any exceptions that they're going to deliver at the barrier or earlier, and that then subsequent instructions can be issued. So if you write a program with no trap barriers, it runs at vector-like speeds, and you get information on something like an overflow that it occurred, but not very precise information on where it occurred. If you do something like put a trap barrier at the end of every subroutine, that may involve draining a few cycles of the pipeline at the end of the subroutine, but it then localizes where the exception occurred to which subroutine. If you put the trap barrier at the end of every source language statement, you can localize the generation of an exception to which statement it was. And if you put a trap barrier after every single instruction, you can discover exactly which instruction generated it. Because the IEEE floating point standard has an extensive set of exception handling, we also included in the architecture manual a design that allows one trap barrier per basic block rather than one per instruction, and still allows complete IEEE exception handling to be performed in software in the trap routine. The basic idea is that there's a software constraint that the compilers not reuse registers within a basic block or not reuse registers before the trap barrier, so that a software handler can successfully backtrack through the instruction stream, find out which exception occurred first, process that exception, and then continue. That allows a substantially faster implementation than stopping after every single instruction and waiting for any exceptions to occur. In addition to the trap barrier, we included exception-enabled disable bits in every instruction, so that integer add, for instance, can be specified in the instruction to take an overflow trap or not to take an overflow trap. That allows languages such as Fortran that require overflows to be generated to simply compile into the instructions to do the overflow, and also allows languages such as C, which generally specify no overflow trapping, to compile into the instruction not to overflow. In a similar way, for floating point underflow, disabling the underflow allows a program to simply give a result of 0 and keep going. Some of our customers have expressed a preference for that behavior. The whole point here is that by choosing compiler options, you get to choose what level of performance and what level of precision on exceptions you want, rather than me choosing for you. So in summary, on the arithmetic exceptions, we rejected an architecture that would require hardware implementations that issue multiple instructions, silo register values, and then have to roll back if an exception occurs. We also rejected implementations that read operands and then check whether an overflow or something could possibly occur, and if so, delay issuing other instructions into the pipeline until the exception decision has been made. That doesn't work for multiple issue, and it doesn't work well for single issue if the read of the registers and the check of the values is actually 2 or 3 stages down the pipeline. Another problem we looked at was memory latency. Over the course of a few decades, main memory latency will get longer and longer as processor speeds get faster and faster, but memory chip speeds don't. So we included in the architecture a pair of prefetching instructions as hints to an implementation. For example, a Fortran program working down one column of an array could issue the prefetching instructions to be prefetching the second column of the array during the processing of the first column. It looked likely that those instructions could bury about 100 cycles of memory latency in a realistic way. We also looked at memory latency in multiprocessor systems. We specified that there is no implied read-write ordering in the following sense. If one processor issues a sequence of reads and writes, they are allowed to arrive at a second processor in an arbitrary order. Implementations are allowed to rearrange reads and writes. That's an enabling technology that allows things like write buffers or multi-bank caches or routing networks between processors if you have lots of processors, or things like memory buses that do error detection and retry. For example, if you have a processor that does 2 writes and you pipeline those writes down a memory bus and the first write arrives with bad parity, the second write then arrives, and then the first write is retried and arrives successfully with good parity on the second try. That's an example of a good implementation technique that has the effect of delivering the writes out of order to another processor. We wanted to allow implementations to run at very high speeds. Therefore, in the architecture, we do not require precise read-write ordering. Instead, there's a memory barrier instruction that says, at this point I care. At this point, all the reads and writes that have been issued by a given processor in front of the memory barrier have to be delivered to other processors before any reads and writes issued after the memory barrier. Now, the phrasing is chosen carefully. It doesn't say that the sending processor has to stop issuing instructions or run slowly. It simply says that whatever permutation could occur in the implementations, that there is a restriction at the memory barrier. And that may mean, for instance, that the memory barrier itself is pipelined out along with reads and writes to other processors. Or it may mean exactly at the memory barrier, a pipelined memory bus sends a write and then waits a few cycles to get confirmation that that write arrived successfully before sending writes that come after the memory barrier. So we view this as an enabling technology for very high-speed implementations. It's one of the design ideas that led Cray Research to choosing the alpha architecture for building a 1,000 processor or bigger, massively parallel processor. So in summary, on the memory system design, we rejected things like implicit read-write ordering in favor of explicit programmer statement of where overlap can occur and where overlap must not occur. So the alpha architecture is a new 64-bit architecture designed to last a long time, designed to allow high-performance implementations, with specific emphasis on allowing multiple instruction issue, multiple processors, and very fast clock rates. The architecture supports a very wide range of operating systems and compiler languages. Some of you who looked at earlier tapes in this series may have seen Dave Patterson when he predicted that by somewhere between 1993 and 96 there would be super microprocessors running anywhere from desktop to supercomputers. We're very happy with Alpha to deliver on Dave's prediction a year early. I think now it's time for Dirk to talk about the first implementation.
As Dick said, I am here to tell you about the first alpha implementation, which internal to DEC we refer to as EV4. Since I'm going to use that term throughout this presentation, first a couple of words on the term. When the program started, the original name for the architecture which the designers came up with was EVAX, for extended VAX, which turned out in retrospect to be not a very good name because the architecture in fact has no formal relationship to the VAX architecture. However, we're engineers and not marketing people, so that was the name we chose at the beginning. It was later changed to Alpha. The name of the chip, however, has remained EV for extended VAX 4 because it was built in a 4th generation CMOS process. The presentation that I'm going to give has 4 basic parts. First of all, I'm going to describe some of the overall features of the chip. Then I'm going to describe some of the higher level architectural features such as the pipelines, the functional units, and the instruction issue rules. I will next describe just a couple of the more interesting microarchitectural features in EV4 and relate those back to the higher level architectural concepts that Dick described previously. And finally, I will talk a little bit about the electrical interface between EV4 and the systems into which it's designed. EV4 is a single chip implementation of the alpha architecture. It's implemented in CMOS technology and has 2 cycle time variants, the first of which operates at a 200 megahertz internal clock rate, and the second variant operates at 150 megahertz. Now these 2 speed variants don't really represent separate designs. They really represent distinct speed bins, so that it's one design and various chips happen to fall in one speed bin or the other. Some work faster than others, and the ones that run fast, we run fast. As I said, the chip is built in a CMOS process. It's built in Digital's CMOS 4 technology, which means that it's our 4th generation CMOS technology. This technology features 0.7 micron drawn feature sizes with a 0.5 micron effective channel length. It also features 3 layers of metallization, and the technology is really focused towards high-speed microprocessor implementations. For example, the 3rd layer of metal is different than upper layers of metal in other CMOS technologies, where the metal is intended to maximize signal routability. In this case, we use a 3rd layer of metal solely to distribute power and our internal high-speed clock, and therefore it's a much thicker, coarser metallization level, which can both bring a lot of power into the chip and distribute the clock with minimum skew. The die physically is fairly large. It's about 14 millimeters by 17 millimeters in size, and it implements about 1.7 million transistors. The part is packaged in a 431 pin grid array, of which 291 pins are signals. The remaining 140 are power and ground. The chip dissipates 30 watts at 200 megahertz or 23 watts at 150 megahertz. It implements a 43-bit subset of the architected 64-bit virtual address space. As Dick mentioned previously, implementations are allowed by the architecture to implement a subset of the 64-bit virtual address. However, the entire 64 bits is checked. The chip also supports a 34-bit physical address space, giving us the ability to address some 16 gigabytes of physical memory. The chip is a superscalar implementation in the sense that it can issue at its peak 2 instructions in each CPU cycle to any one of 4 fully pipelined functional units. The functional units include an integer operation unit, a floating point operation unit, a load store unit, and a branch unit. The chip also includes a total of 44 translation look-aside buffer entries, 32 of which are dedicated to data stream references, and 12 of which are dedicated to instruction stream references. Both translation buffers are fully associative. There is an on-chip write buffer, which includes 4 entries, where each entry can contain 32 bytes of data. The chip also includes 2 on-chip caches, 8 kilobytes in size, 1 devoted to instruction stream references and 1 devoted to data stream references. Both of them are physical direct map caches. The data cache is write-through. The bus interface is flexible and can support system designs with either 128-bit or 64-bit data paths between the system and the chip. And as previously mentioned, the external interface supports a 34-bit physical address. The next graphic shows a crude block diagram of the chip. Starting from the top, you see an instruction cache, which each cycle can feed 2 instructions to the I box, or instruction issue unit of the chip. The I box is responsible for decoding the instructions, performing all on-chip resource checks, and sending the instructions off to the respective functional units. The E box is the integer operate unit, which performs basic integer operations such as add, subtract, or and shifts. The F box is the equivalent floating point operate unit. The integer register file sits below the E box, while the floating point register file sits below the F box. The diagrams in the picture represent data buses, which contain data flowing to and from the functional units from the register file. You can correlate Dick's discussion of the instruction formats laid out in the alpha architecture to the physical orientation of the chip itself. From the top of the integer register file, you see 2 64-bit wide buses which carry integer operands to the E box, and another 64-bit bus which carries integer results back to the integer register file. Similarly, on the floating point side of the chip, you see 2 64-bit buses which carry operands to the floating point functional unit, and another 64-bit bus which carries results back to the register file. Below the register files sits the A box. The A box fundamentally is the load store unit within the machine. You can see 2 register file ports feeding the A box. One of these contains base addresses. The other contains stored data coming from the integer register file. Similarly, on the floating point side, you see a single 64-bit wide bus which carries floating point stored data out to the A box. Below the A box is the 4-entry by 32-byte wide write buffer, which gets its data from the A box and supplies data out to the BIU, or bus interface unit. And lastly, at the bottom of the diagram, you see the on-chip data cache, which, as I previously stated, is 8 kilobytes in size and a write-through cache. The bus interface unit is responsible for orchestrating activities between on-chip functional units and the outside world, meaning the system. It contains a 64-bit data path which carries both fill data from the off-chip memory structures to the on-chip primary caches, and also carries write data from the write buffer out onto the pins. The next graphic shows the integer pipeline of the machine. It is 7 stages long, and this diagram can be used to describe the pipelines which operate in the I box, the E box, and the A box. Taking the I box first, you see fundamentally 4 pipeline stages. In stage 0, which we also refer to as the instruction fetch stage, the I box reads a naturally aligned pair of long word instructions from the instruction cache. In the next cycle, the I box performs 2 primary functions. First, it decodes a portion of the instructions in order to determine which functional units the instructions should be sent. In parallel with that, it determines for branch instructions the probable target for the branch. The chip supports 2 methods for branch prediction. In the first method, we support the architected hint alluded to by Dick earlier in this talk, where the hardware looks at the sign bit of the displacement field in the branch instruction itself and predicts that backward reaching branches are taken while forward branches are not. Alternatively, the chip also implements a dynamic branch prediction structure in which, associated with each instruction in the instruction cache, is a single bit. This bit indicates which direction the branch took the last time it was executed. When new instructions are brought into the instruction cache, we load this bit with the sign of the displacement as an initial guess, and then this bit gets updated later. Branches which are predicted by the hardware to be taken result in a 1-cycle bubble being inserted into the pipeline, meaning that if a branch instruction is fetched from the instruction cache in cycle 0, it takes all of cycle 1 to predict the direction of the branch and generate the target for the branch, so that we are not able to go back to the iCache for that target until what would be cycle 2 for the branch. This bubble, which gets inserted into the pipeline, can in some cases be removed later. In pipe stage 2, labeled I0, we perform more instruction decode. And in pipe stage 3, labeled I1, all the real action takes place. In that pipe stage, we read operands from the register file and perform resource checks to see whether the instruction can be issued. These resource checks include both the availability of register operands as well as the availability of the on-chip functional units. After pipe stage 3, instructions either execute to completion and write the results in the register file, or perhaps they get aborted for a host of reasons which I'll describe later. Within the iBox, there's still a few more activities that happen later down the pipe. As Dick mentioned, conditional branches test a register in order to decide whether to take the branch. Since we read the register in cycle 3, we can test its value against 0 in the beginning of cycle 4 and be in a position to determine whether the branch should in fact be taken or not. Notice then that although a branch instruction is fetched from the instruction cache in cycle 0, we don't know whether it's going to be taken until cycle 4. What this means is that if the branch was predicted incorrectly, we incur a 4-cycle penalty to go back and get the true branch target. Also in cycle 4, we're in a position to generate the true virtual PC for the instruction 1 stage back in the pipeline. So we have this virtual PC at the end of pipe stage 4. In pipeline stage 5, we can, from this virtual PC, generate the corresponding physical PC so that at the end of pipe stage 5 and the beginning of pipe stage 6, we can determine whether the instruction that we fetched 5 cycles ago, in fact, hit in the instruction cache. So this means that if an instruction fetched in pipe stage 0 missed the cache, we don't know it until 5 cycles later. Moving on to the activities which happen in the E-box, I'll start in pipe stage 4. In that pipeline stage, the E-box has two 64-bit operands on which to perform an operation. Most operations in the E-box can be performed in a single cycle. These include add and subtract and the simple logic functions like add, and XOR. So at the end of pipeline stage 4, the results of these instructions are ready for use by subsequent instructions, although the results won't be in fact written to the register file for 2 more cycles. We can supply the data on bypass paths back to a multiplexer which physically sits between the integer register file and the E-box. Shift operations take 2 cycles to complete. The results of shifts are therefore available in pipe stage 5. Shift operations therefore have a latency of 2 cycles, although they can be fully pipelined. Also in pipe stage 5, we produce, based on the results generated in the E-box, a bit which indicates whether that result is 0. We then store that bit in the register file. This makes branch instructions easier to execute. Lastly, in pipe stage 6, the E-box writes its results into the register file. Now, referencing the same diagram, I'm going to describe the operations which occur within the A-box. The A-box receives its instructions issued from the I-box at the end of pipe stage 3. In pipe stage 4, it takes the operand supplied to it from the register file and adds to it the displacement. Thus, at the end of pipe stage 4, it has an effective virtual address. Because the size of the data cache is equal to the size of the pages used by the memory management system, we can start looking in the D cache at the beginning of pipe stage 5. We don't have to wait for the translation buffer to produce a full physical address. Therefore, at the end of pipe stage 5, we have in our hands the physical address that corresponds to the generated virtual address and the data which hopefully corresponds as well to that virtual address. We are in a position to know whether a load instruction actually hit or missed at the beginning of pipe stage 6. And if the instruction hit in the data cache, we can supply the results of the instruction to the functional units by the end of pipe stage 6. Hence, load instructions which hit in the data cache have an effective latency of 3 CPU cycles. For stores, we know as well at the beginning of pipe stage 6 whether the store instruction hit in the data cache. If it missed, no further operation is required for the data cache. The data is moved into the write buffer independent of the results of the data cache lookup. If the lookup resulted in a data cache hit, we write the corresponding data into the data cache array the next time that that array is otherwise not busy. Turning next to the diagram which shows the floating point pipeline, you see that floating point instructions share the first 4 pipeline stages with integer instructions, and those really correspond to activity which I previously described in the I-box. The floating point pipeline is quite a bit longer than the integer pipeline, and floating point results are not available until 6 CPU cycles after the instruction was issued. The floating point unit is fully pipelined, however, so that we can start a new floating point operation every CPU cycle. However, as I said, the effective latency of this functional unit is 6 CPU cycles. Now I want to talk about the instruction issue rules which hardware within EV4 enforces. Generally, if you think back to the diagram which showed the functional units within the chip, you can see that the possibility for multiple instruction issue is certainly there. We have 4 fully pipelined units, and the I-box ought to be able to issue pairs of instructions to any of these units, and generally that's the case. We can issue load or store instructions with operate instructions. We can issue integer operate instructions with floating point operate instructions. We can issue floating point operate instructions with corresponding floating point branches, or integer operate instructions with integer branches. One quirk is that integer stores can't be issued together with floating point operates, nor can floating point stores be issued together with integer operates. This is due to an internal hardware resource constraint in the iBox, which, although not real difficult to get around, wasn't worth the added complication in terms of the performance that it would have bought us. Next, I want to address a couple of interesting microarchitectural features which we included within the EV4 chip. The first of these addresses the branch latency problem which Dick referred to earlier. Specifically, it addresses the problem associated with memory format branches. These instructions are used in computed jumps, subroutine calls and returns, and the like. The instructions read the register file and jump to the virtual address contained within the operand register and represent a special problem for the instruction prefetch hardware. Thinking back to the earlier diagram which showed the machine's pipeline, remember that the branch prediction hardware runs in pipe stage 1 of the machine, while registers aren't read until 2 cycles later. Therefore, in order for the prediction hardware to come up with a target for the branch, something has to be done in hardware if we want to come up with a target early in the pipe stage, since the actual target isn't available until pipe stage 3. The solution here is to implement what we call a JSR stack. This stack allows subroutine and call and return addresses to be maintained back in the pipeline by the instruction prefetcher, and also requires use of hint bits. On a subroutine call, the compiler inserts into the instruction a 2-bit field which tells the hardware that this instruction is actually implementing a subroutine call. The prediction hardware then takes the virtual address following the subroutine call and places that on a hardware stack. When the subsequent return comes along, we then pop that stack and use that as a target for the instruction. This JSR stack has a depth of 4, meaning it's capable of holding at any one time a stack of 4 subroutine return addresses. We also include hardware to make sure that this stack doesn't get corrupted. The way it might get corrupted is as follows. We could fetch from the instruction cache an instruction that's a call. We might then send this instruction down the pipeline, and later, for whatever reason, an exception, a branch mispredict, an instruction cache miss, the call instruction may never get executed. If we updated the stack when we fetched the instruction rather than when we committed to executing the instruction, the stack could therefore get out of sync with the rest of the machine. Note that this is a performance optimization, and if the hardware stack ever gets out of sync with the real program flow, we do not end up with incorrect operations. We merely take a little bit longer to fetch the target of a call or return. The next feature that I want to describe relate to granularity hints. The alpha architecture uses a 2-bit field within each page table entry, which can be used by software to communicate to hardware that a particular page table entry, in fact, maps greater than a single page. This 2-bit field can be used by the software to communicate to the hardware that a given page table entry, in fact, maps a contiguous physical region consisting of 1 page, 8 pages, 64 pages, or 512 pages. Since EV4 implements an 8 kilobyte page, this translates to a region of 8 kilobytes, 64 kilobytes, 512 kilobytes, or 4 megabytes in size. The data stream translation buffer contains 32 entries, as I previously stated. Each of these entries is able to support any of the 4 granularity hints specified by the architecture. This allows a very flexible arrangement for page table entries and also allows a relatively small associative translation buffer to in fact map a large memory space. The size of the page mapped by each entry is set when the page table is written by PAL code into the translation buffer structure. The iStream translation buffer consists of 12 entries. 8 of these entries are devoted to the smallest granularity size, meaning that each of those 8 entries can only map an 8 kilobyte region corresponding to a single page. 4 of the entries, however, support the largest granularity size, which means that each of those entries can map a 4 megabyte region. This is very useful for mapping large, non-paged instruction areas, such as the operating system kernel or large shared libraries. I'm next going to describe EV4's external interface. This interface was designed with several goals in mind. First of all, we needed the interface to be extremely flexible. Since this is the first chip in a new architecture, and since we didn't have the resources inside the company to devote several design teams, each to doing an implementation targeted towards a particular end of the system-wide spectrum, this single design needed to be used in systems ranging from low-end desktop machines to mid-range multiprocessor servers, all the way up to high-end, massively parallel supercomputer systems. With that in mind, we needed each system designer to be able to make his or her own cost-performance trade-offs. Lastly, because of the schedule constraints confronted by our internal system partners, we wanted to define an external interface around which you could design a system using off-the-shelf industry-standard components. The next graphic shows a crude schematic for the external interface of the EV4 chip. The chip takes as its input a 2x clock. So, for example, a chip that operates internally at 200 megahertz requires a 400 megahertz input oscillator. This is the only high-speed signal that a system designer really has to worry about. The rest of the interface can be programmed to operate much more slowly. The chip also supports an external cache, although this cache is not required by the chip design itself. Its presence or absence is left solely up to the system designer. For systems which do implement an off-chip cache, the chip is capable of accessing that cache with no help from external system-level logic. So, for example, if a load instruction misses the on-chip cache, the on-chip BIU can read the off-chip cache RAMs with no interaction from the outside world. This relieves the system designer from having to design logic which has to directly interface to the high-speed clocking domain inside the chip. The graphic shows 3 RAM structures which make up the external cache. The tag control RAM consists of 4 bits, a valid bit, a shared bit, a dirty bit, and a parity bit, which contains parity across the previously mentioned 3 bits. The tag RAM contains a tag corresponding to each block in the external cache, and the data and check RAMs contain the cache data and associated check or parity bits. As I previously stated, the external bus can be either 64 bits or 128 bits wide, as determined by the system designer's needs. To begin a cache reference, the chip drives an address out onto its address bus. This address and associated RAM control flow through system-dependent logic which physically sit between these buses and the RAMs. The RAM access is completely combinatorial. The chip drives a new address out onto the RAM and then waits a user-specified period of time before sampling the associated tag and data fields. Some external transactions cannot be required by EV4 alone using the external cache RAMs, and for these transactions, system-level components have to get into the picture. Information between EV4 and these components flows between the miscellaneous control field listed on this graphic. This field consists of a command field onto which EV4 drives commands such as read, write, memory barrier, load locked, etc., and a pair of acknowledgement fields which system-level components drive back to EV4. These control fields operate synchronously with the internal chip clock, but phase-aligned to a system clock which is programmable. This system clock can be user-specified to operate at frequencies ranging from half to 1/8 the on-chip CPU cycle time. In keeping with the previously mentioned external interface goals of performance, flexibility, and simplicity, EV4 supports external caches ranging in size from 128 kilobytes to 8 megabytes, or, as I previously said, we could have no cache at all. The external cache, if implemented by the system designer, can be built with a variety of industry standard RAMs. High-end systems can use the fastest, largest static RAMs they can buy, while low-end systems can use smaller, cheaper, slower RAMs. The RAM timing is set by software and can range from 3 cycles to 16 CPU cycles, determined by the value which software places into an on-chip control register. The external interface, although it runs synchronously to the on-chip CPU clock, can be specified to run anywhere from 1/2 to 1/8 the speed of this on-chip clock, again allowing cost-performance trade-offs to be made by the system designer. Lastly, there are no cache policy decisions enforced by the EV4 chip. This means that it's left to the system designer to decide what cache coherence protocol is appropriate for him or her. The valid, dirty, and shared bits, as I previously described within the tag control field, imply a bias towards a conditional write-through cache coherence protocol in name only. Really, the shared bit simply specifies to EV4 that it cannot write to an external cache block by itself, but requires external module-level interaction in order to complete the write. This means that in addition to a conditional write-through protocol, the system designer could implement a pure ownership coherence protocol, where the shared bit becomes really more of an ownership bit, or the system designer could implement a pure write-through protocol, where the shared bit is always set. This means that EV4 will always request help from module-level components before writing data into the external cache. The external interface also allows the system designer to implement either a 128-bit wide or 64-bit wide external bus. The chip supports both CMOS TTL and ECL levels and supports both long-word error-correcting codes or long-word parity. The chip does not perform on-chip invalidate filtering for decache invalidates, but does provide a mechanism so that system designers can filter these invalidates off-chip by implementing a backmap. Here's a die photograph of EV4. On the left is the 8 kilobyte instruction cache with the branch history table located just below that. Across the top of the die you see the instruction execute unit with the E box on the left and the I box on the right. In the middle of the chip you see integer control with the clock driver extending horizontally across the center of the die. Below the clock driver is located the floating point operate unit, while the data cache occupies the right edge of the die. The write buffer can be seen in the upper right-hand corner. In conclusion, EV4 is the first implementation of the alpha architecture. It's a 200 megahertz single-chip microprocessor with a flexible interface to allow it to be used in systems ranging from desktop workstations to massively parallel supercomputers. It will be supported initially by both VMS and OSF1, with other operating systems to follow. And it's the first in a family with more implementations to come. Speaking as a hardware system designer, I'm grateful for people like Dick Seitz, who has thought long and hard about the problems faced by high-performance system designers when designing the alpha architecture. I think that the advantages of this architecture are apparent by the high performance achieved by its initial implementation, and the advantages will become even more apparent in the future. I hope this tape has been beneficial to you, and thank you very much.
Isn't that wonderful?
Okay, lights.